Okay, so this is a talk about cylindrical coordinates, velocity, and acceleration. I'm going to use, in a cylindrical representation, we have an angle and a length. So the length of a vector given by r theta. So we can write that a position vector r is the length of that vector times a unit vector in the direction of that vector. This is our starting point. If we're to look at the velocity of a vector in a cylindrical representation, we just have to take derivatives. So we can do that. dt, dr dt is, by chain rule, dr dt r hat plus r dr hat dt. Or for short, we can say r prime r hat plus r hat prime. We can take second derivatives, and that will be r prime r hat plus r hat prime again. So we have r double prime r hat plus r prime r hat prime plus, taking derivatives here, we have r prime r hat prime again plus r hat double prime. So we have two of these guys. Now, we want to give a specific meaning to the unit vector derivatives. So let's figure out what those are. So, in geometric algebra, we can write the unit radial vector as e1 times the exponent of e1, e2, theta. So that is e1 cos theta and e2 sine theta. So if you expand this out, you have e1 times cos theta plus e1 e2 sine theta is e1 cos theta plus e1 squared e2 sine theta, but e1 squared equals 1, so we have e1 cos theta plus e2 sine theta, which is what I claimed here. So we have a fairly simple representation for unit radial vector in cylindrical coordinates. Slide the board up. Now, this almost has the look of complex variables. So we're going to make it look like complex variables if we write I equals e1 times e2, or sometimes as e1, 2 for short. So if we do that, we now have r hat equals e1 times e to the I theta. The caveat here is that e to the I theta and e1 don't commute. In particular, this equals e to the minus I theta e1. That holds for any vector. So any vector in the plane of e1, e2. So if we say that a is in the span of e1, e2, then a e to the I theta equals e to the minus I theta a. That's easy enough to show, but it's an important difference compared to complex numbers, because we have to keep the order. The order has to be kept track of. We don't have the commuting property. So with having defined r hat, now we can easily take the derivative r hat prime. So that is e1 I e to the I theta, writing it out in full, e1 times e2 e to the I theta. Now e1 is 1, so we're left with e2 e to the I theta. So that is r hat prime. Oh, sorry, I missed d theta dt. So now this guy is our theta cat vector. So we have r hat and theta hat. Theta hat is e2 e to the I theta. And we should expect r hat and theta hat to be perpendicular, and we can do a quick check of that. So, geometric algebra, we can, if we have two vectors, A and B, we can compute their dot product by selecting the scalar grade of the vector product of A and B. And that turns out to be a really easy way to compute a number of different dot products. So let's use that to compute the dot product of r hat and theta hat. So r hat was e1 e to the I theta, and theta hat is e2 e to the I theta. The scalar grade of these two is their dot product. So we can switch the order of these two, introducing a conjugation and the sign of the complex exponential. So that is e to the minus, actually I'm going to do it the other way around. Let's switch the order of these two. So let's write this as e1 e to the I theta, e to the minus I theta, e2. Now, these cancel out. We're left with what is the scalar component of the product e1, e2. Well, e1, e2 is a bivector, has no scalar product, no scalar component. So that's 0. R hat dot theta hat is 0, just as we'd expect. If we wanted to write out theta hat specifically, we can do that. E2 times cos theta plus E1, E2 sine theta. That is E2 cos theta plus E2 times E1 times E2. Switch the order of this and conjugate, and so that is E2 times minus E2 E1 sine theta. E2 times E2 is 1, so we're left with E2 cos theta minus E1 sine theta. Let's go back to the velocity and acceleration. So we have r hat, so we had r prime, the velocity, was r prime r hat plus r hat prime, and we've just figured out that r hat prime is theta hat, so we now have r prime r hat plus r theta hat. R prime was theta hat d theta dt, or omega theta hat. So r omega theta hat. And this here, if you have circular velocity where r hat prime equals 0, then you have v equals r omega theta hat. And you'll often see this in the physics textbooks written in scalar form, saying v equals r omega. For the acceleration, actually, before we go on to acceleration, let's look at a different way of looking at the components of the velocity. So the components of the velocity, we can write the velocity as velocity times 1, that's equal to 1. So that is velocity the product of velocity times the radial vector, all times the radial vector. Now we can write v dot r hat plus v wedge r hat. So now we have correspondence between the projective description of the velocity and the derivatives. So that is v dot r hat dr dt, and v wedge r hat is r d theta dt theta hat r hat. Now if you multiply this all out on the right by r hat, the r hats cancel, so you would have v wedge r hat, and that is the correspondence. Now this is also equal to theta hat wedge r hat, since theta hat r hat equals 0. So we have v dot r hat equals dr dt, and v wedge r hat equals r d theta dt theta hat wedge r hat. So there are geometrically, these are related to the projection and the rejection with respect to r hat. And we see that the radial component of the velocity is just dr dt, but then the radial bivector is in the plane of theta hat and r hat, and has the magnitude of r d theta dt. Just two different ways of looking at the same thing. That it's have a specific example of something physical, the azimuthal component of the velocity, and how that relates to a bivector. Let's now look at the acceleration. So for r hat double prime, the acceleration, we had r double prime r hat plus 2 r prime r hat prime plus r hat double prime. And we can write that out. R double prime r hat plus 2 r prime omega theta hat plus r omega theta hat prime. So you need second derivative of theta hat to start with, or first derivative of theta hat, and that is e to the I theta prime, which is e2 e1 e2 e to the I theta d theta dt, this time not forgetting my d theta dt, and that is minus e1 omega e to the I theta, or minus omega r hat. So the acceleration has an inward radial component, the centrifugal force, if you'd like to call it that, and it's directed with magnitude omega. Let's plug everything back in. So I'm going to slide the screen up there. Sorry, I had a pop-up that probably didn't show at your end. That was annoying. Okay, so we have the acceleration is r double prime r hat plus 2 r prime omega theta hat plus r omega prime theta hat plus r omega theta hat prime, which is minus omega r hat. And we can group terms. So that is r hat times r double prime minus r omega squared plus theta hat times 2r prime omega plus r omega prime. Now, this term is often rewritten as r squared omega prime with 1 over r. So we have 2r squared divided by r, which is 2r prime omega plus the r omega prime divided by r squared omega prime divided by r, which is the r omega prime. So we can slide up and have radial component of the acceleration and plus a theta hat component. So there is our acceleration. Let's also look at the acceleration in terms of its projections with respect to the radial unit vector. So if we say a, the acceleration equals a times r hat times r hat. This is using the fact that r hat times r hat equals 1. So that is a dot r hat plus a wedge r hat r hat. So now we can say, all right, the radial component of the acceleration is r double prime minus r omega squared, and the bivector describing the azimuthal component of the acceleration is So here are projection and the rejection breakdowns of the acceleration. And so you could write these in terms of the cross product if you like, because you have, let me slide this up. The last formula could be written in terms of cross products, because we can say A cross B, I A cross B is A wedge B, and we'd end up with an I on either side. If we plug that into both of these wedge products, the A wedge R and the theta wedge R, so that allows us to write A cross R hat goes 1 over R theta hat cross R hat. Now, in order for this to be meaningful, we now have to work in R3. Whereas before that, this works in R2, or it works in Rn. You may or may not ever care about acceleration velocity in any spaces other than R2 and 3, but if we use the wedge product representation of the acceleration, call it an acceleration bivector, angular acceleration probably, then the wedge product is a universal representation for the same concept without introducing a third dimension that may not apply to the problem. And in Rn, like R4 for example, there's no well-defined unit normal to any given plane, so describing something in terms of the cross product just doesn't work. Anyways, that is all of what I wanted to present in this talk. Thank you for listening. Bye-bye.